Okay, I want to talk about two-dimensional angled takeoff problems. And I've got in this circumstance, I've got something, I don't know, throwing a ball, 50 meters per second at an angle of 30 degrees. And let's first visualize what's happening. This ball is going to go up and it's going to come down. And most of the time we're asking, let's just assume this is right on the ground there. Most of the time we're asking what delta x is. But occasionally we could ask what delta y is. We know what delta y is at the end. It's 0, right? It starts and ends at the same height if it's like this. But we could ask what this delta y is. So that's the basic layout of the problem. Now, to do this, once again, we do not deal with things going in that shape. We don't have equations for that right now. What we do have is one-dimensional equations. So we have to separate this out so it's two one-dimensional problems. Let me get rid of some of this, make it a little clearer here. Okay, first step to, I'm hoping nobody's surprise, is to have a frame of reference. I'm going to call that my y, and I'm going to call that my positive x. Second thing I'm going to do is I am going to break this angled vector up into two components. One like that, one like that. Okay, they should have arrows on there. Let me draw arrows on there. Right like that. Okay? That is how fast it's going right to left and how fast it's going up at the very beginning only. Because remember, as gravity acts on this, it's not going to be going up as fast. It's going to slow down, slow down, slow down, and then speed up in the other direction. Well, this one, I'll just write it out once. 50 cosine of 30 is 43.3 meters per second. So it's going to the right, 43.3 meters per second. 50 sine of 30 ends up being 25 meters per second. Okay? Once I've done that, I can just get rid of, this is dead to me now. I don't care about that anymore. What I've got is something that's going 43.3 meters per second, constant velocity, right, horizontally, and 25 meters per second at the beginning in the vertical dimension, and I know there's going to be an acceleration, constant acceleration in the vertical. Okay, so let's do it, horizontal and vertical. What I like to do, and I didn't do it in the last one, but because I wanted to really just show you, you can just write things in different parts of the paper. But what I like to do is here have horizontal or X and vertical and Y. So you could either do H and V, or you could do X and Y. I don't care. You don't have to do it this way at all. You can just write separate equations. But what's very, very important is to never let the horizontal and vertical variables cross-contaminate, because that'll cause you so much trouble. The part of this business of orthogonality and independence is that no matter how fast it's going, this could be a million meters per second, it's not going to affect the up and down motion. And this could be really fast or really slow, it's not going to affect the right-left motion. It's only each of those will only affect the other through the time in the air, changing the time in the air. Okay, so let's fill out our variables. So step one, break into components and pick your frames of reference. Step two, start listing variables. Horizontally, it's pretty easy. Once again, I tend to write, I'm looking for delta x. I know the average velocity is 43.3. That's positive. There you go. Meters per second. And I kind of know that I'm going to need the time. I'm going to write that down at the bottom. It's neither horizontal nor vertical. Well, I don't have enough horizontal stuff to solve for time. So let's go to the vertical. Okay, delta y for the whole trip, and this is really important. I'm going to write down here, whole trip. Okay, the whole up and down, you know. For the whole trip, delta y is 0. Right? It starts at the ground, it comes back to the ground. My initial velocity, my v0, is 25. My acceleration, just like we did with the horizontal ones, is 10, but notice, since I picked up to be positive, it's negative 10. So you always have to be aware of that frame of reference. Okay, if you tried to solve this for time, you would come up with 0 and another number. You'd come up with two solutions because there's a t squared in that equation. What I would recommend is rather that, and that kind of shows that at the beginning it's a delta y of 0. So it'll give you two solutions. What I tend to do is this. There's one easy variable in here. Remember what we talked about when you throw something up, when it comes back to the same height, there's a symmetry, -25. So I get this from breaking down the velocity vector. This is essentially given for the whole trip. This is a given. But this is one that you can, just by knowing physics, put in there. That final velocity, when it gets back down to the ground, only when it gets back down to the ground, not up at the top, not if it were going off a ledge, but if it's going back to the ground, it's -25. If you use this, now you've got four variables. Almost any equation will help you, but let's assume you use A equals V minus V0 over T. You'll find that time is 5 seconds. It's actually really easy because look at that. Remember, it changes by 10 meters per second. So it goes 2.5 seconds up, 2.5 seconds down. It changes by 10 every second, 2.5 seconds to change by 25. Once I've got that, 5, and I've got V, and again, you could do this acceleration stuff using an acceleration equation. I'm showing you, you can do it in your head. That's how easy it is. V equals delta x over t, and so we have 5 times 43.3. I think that ends up being 216 meters. Okay. Now, what I'm going to do is I'm going to then ask the question about, now I need to change colors here. I'm going to go purple. I like purple. Now I'm going to solve this, delta y. Okay? So now we're no longer talking about the whole trip. We're now talking about half trip. Right? Because that happens halfway into the entire story. Well, there's a few things. First of all, V0, yeah, that's okay. A's okay. This V's okay. Delta y is no longer 0. I got to get rid of that. V final is no longer -25. X is no longer 216. But there are some free things here. First of all, picture just the vertical motion. You throw a ball up at 25 meters per second straight up in the air. What happens up at the top? It has a velocity of 0, if I can get my pen to work. Right? So now, oh, I'm sorry, and this is no longer 5. It's actually 2.5. It's half of the trip. So now I can use these variables to solve for delta y. Okay? I'm not going to do that right now, but I just want to show you how you set up those two types of problems. So for any of these angled problems, in fact, for any two-dimensional problems, these happen to be special ones. They happen to be projectile motion where we're near Earth. But you could have a two-dimensional 2D problem where you had a rocket and maybe it's got like a little blaster on the side. And so it has a certain acceleration in that direction, has a certain acceleration in that direction. So I would still break it up into x and y, but now the x would have an acceleration. But you can always separate these things out into horizontal and vertical. I shouldn't say horizontal and vertical, I keep saying that, into perpendicular problems. But be very, very careful about making sure you get the right variables for each dimension, and it's no harder than a one-dimensional problem.